So I welcome you all, and we are back with the structural analysis of using energy methods, right? So this is a new topic actually. So this we'll call the, in other terms, energy method of analysis, and basically we'll be discussing two uh, two concepts of this, right? Using virtual work method and Castigliano's theorem, right? So in this approach, both gives the same answer, but they are different from their fundamental aspect. And here as well, this virtual work method can be divided into several parts, but here we only focus on two aspects, but we will only use one aspect of that, right? So this will be basic, most of the time will be used. Okay, so I'll discuss what's that. And for the Castigliano theorem, so you can actually link these two together uh, in same equation. I'll show you how. And first we'll discuss, uh, we'll call a structure, a beam, truss, or we'll call a truss element. Okay, so let's discuss a truss like this, right? Okay, so if I apply a load, right? If I apply a load to this point, right? So what happens is this truss gets deflected, right? It will be your finally the truss will be like this, right? Right. So what happens is you will have this point. Okay, they consider about this point is now here, right? So this deflection, let's say delta f. Okay, okay, deflection, let's say delta f, and this is a point, right? So this force is taken by the each member of the truss, right? So that means each member will have a contraction or an elongation based on the force component along that member, right? Let's say a member like this, right? Let's call a member like this. So let's say this member, okay? Let's say that will have a force of P, okay? So what will happen is, due to this force, this will elongate from the original position or contract. If it is force is in the other way, right? This will contract from the initial position, right? So based on that, we can tell, let's call this delta. Let's call this delta, right? Okay. So what actually happens is, if you increase this f, right? So this f and your delta is linear, right? So draw a curve like this, and okay, this is your delta and force. So when you increase the force, right? When you increase the force, your delta, right, or is also increases, right? Right. So Let's think this is the moment where it gets F, right? Okay, let's call it Fi. Okay. So at this point, we will say it's delta I. So what you can write is, so force is increasing from the 0 to F1 while the deformation increases from 0 to delta. So if you take a small portion, let's say, so your work done total work done, okay, can be, so let's say some part like this. So the part, so let's say this is uh, uh, delta, okay. This is, let's say, uh, F, okay. So the work done on these deformation, right? Let's say, let's call this F, and this is F plus delta F, right? So let's call this force is really small, okay. So that your force, so the work done on that portion is Wi, let's say, not Wi, I call this W1, okay. So in this small portion, the work done is F into delta, right? So to get the total work done, you need to integrate. So that means really this area, right? You need to integrate it over the length, right? Into d delta, right? So what will basically give you is that area of this triangle, right? Half F into delta F, right? Let's call this delta. Let's call this F and delta F. This is the total work done, let's say. So the total work done is given by this, right? F, right? So this is F1 and F1. Okay. So the total work done is given by this one. So this loading is uh, increased, right? So if it is increased gradually, right? What happens if you increase the load suddenly, right? If you increase the load suddenly, right? You suddenly change the load. So that means load is a constant, right? Almost. You suddenly apply a force, right? So that means your work done is F into delta, right? These are different case. When you suddenly increase the force, this is you gradually increasing the force, right? So know the difference, okay? So this is gradually, this is suddenly, right? So where this work is stored in then, right? So, you know, each member is getting deflected. So that means it has a strain, right? So strain is deformation per the original length, right? So that means when it is contracted or elongated, the work done is stored in each member. In each member, as a strain energy, right? Doesn't matter if you apply a loading at only at one point. So each member is deflected in whatever manner, and then a strain energy is uh, stored in each member. So I'll call the ith member. Okay. So ith member have a strain energy of. So let's say the force in the ith member is Fi. Let's say ith member can be this member, or else uh, the one I'm showing, right? So let's say this is the force, okay, right? So that the deformation, let's say di, okay. So the work done, actually, the work done in this. So you can even write, if you know the, so you know F equals kx, right? So for axial loading, you know, uh, uh, you can, so you have another equation like this, F equals, sorry, that is going to be, uh, so sigma equals E epsilon naught. Right. So epsilon naught is the strain, right? So no need of this for now. So epsilon naught is the strain for an axial loading, right? For axial loading. So we discussed even in this finite element method lectures as well. So sigma is the axial stress. So you can write F over A I. Fi over Ai is the material property. So the strain is, let's say, D1 over L. L. Okay, so you can write Di as FL over AE. So all of them have subscript I, right? So if you need, you can write D as this, okay, function of df, okay? So this is so I have written I from the outside. So each of these have I, Fi, Li, Ai. If the material is different, so that will be Ei. Okay. So whatever strain energy, so you can again write like this, the equation for a member. You can write half Fi into Di, force into displacement divided by 2, right? So the total work done, right? Total work done is this, right? Total work done, right? The original force, external force, right? And the external displacements, right? Is equal to the summation. So this is the strain energy stored in a particular member. So they have a couple of members. So you need to add each member, right? Okay. So that means, right? Okay. So this part is the external work done, right? This part, this is from the energy conservation, right? This part, the strain energy stored, right, in the members. So we consider, so we apply a force, that force external, uh, creating a member force in each member, so that each member force will create a deformation or strain in each member, so that each member will store some strain energy. That is the summation of strain energy of each member will be equal to the total work done by external force, right? Total work done by external force. So that we'll discuss. So we'll be moving first to the virtual work method. Okay. So this is our topic number 8. Okay. So there we can actually do this in two ways, right? So this is the first way. I'll show you the first way. This is the second way. Okay. So what we can do is, let's say this is your truss. Okay. I'll draw it a bit larger so that I will draw the second one in the next slide, because that is important. This is the first one. Okay. So let's say we have force F here applied at this point, and the corresponding deformation is delta F. Okay. And due to this F, this will have forces of Fi, let's say, in this member. All of these members will have some force. Okay. I'll consider only one member and then a representative member. Okay. So what happens is Fi, let's say, so let's say the deformation is Di. Okay. So what we are basically doing is we keep the F as a constant. So we are disturbing the structure, perturbs the structure, right? Disturb. Okay. We are giving some disturbance, perturbation into the structure, right? So how we are going to do that is we apply a deformation to this point while it has already a delta F deformation. Okay. So we'll apply a deformation of, let's say, d delta. So this point has already deformed delta F. So we'll apply, this is the imaginary displacement. What happens if this point is actually another d delta time, sorry, uh, d delta times deformed. So that is hard to see. Okay. So d delta, I'll apply a deformation. Okay. In this way. Okay. So due to this deformation, so force is still a constant. Okay. Force is still a constant. Imagine, assume that. Okay. So due to that deformation, this will also have some strain, right? Additional strain. So this will have some additional, let's say, delta d I deformation. Okay, so what actually happens then? If you draw the curve like this, so this is your force F and deformation delta F. So you are giving an additional displacement of d delta, right? While keeping the force constant, right? While keeping the force constant, right? The force is still constant, so that this will be the additional work done, right? So the external work done will be equal to still F into d delta, right? F into d delta, right? So this is the external work done due to this imaginary displacement, right? So in each member, it will have additional strain energy stored, right? So that will be okay. So that will be how much? So we keep the member forces also constant, right? If this force does not change, this Fi does not change, so that the additional energy stored in each member will be, you have to uh, multiply this Fi by the additional displacement. Okay, it's like this, similar to this. Member force is now simple Fi, you are giving an additional displacement, keeping the force constant, right? So this is for ith member, and you have to sum it up, because you have let's say four members. Let's say this one member, okay, or as five members, 1 2 3 4 5, right? So according to energy principle, so you have F d delta is equal to sigma Fi delta di, right? So this is the first way, right? That you can disturb the structure, right? So actually, this is not actually the W. You can call it even this W delta W, because as an additional work done, right? So this you can take as actually the delta U. So that delta U is equal to delta W, and then you form this equation, right? And the next step is, so keep in remember, in the first method, F is a constant, and which brings you to the second method where delta is a constant, right? So this will be your truss. Okay. So let's say we apply a force F and deformation is delta F, and each will have a force of Fi and deformation of Di, right? So we keep now is the second method, okay? We keep the deformation constant. That's not going to change. Deformation not going to change, okay? So what then we are adding is we apply a delta force, right? Force in this way. We initially apply delta, so we apply a delta F, right, to this way, keeping the deformation constant. This is actually a virtual situation, right? You have to imagine this, right? What if, right? Because no way you can know that if you apply a force, definitely it's going to reduce, deform, right? So your deformation will change. This is a virtual, right? That's why it called virtual work theorem, right? So if let's say if you apply a delta F to the structure while keeping the force, so deformation constant, you can even think it as a uh, small force, right? Very small force. Then if you are, let's say, if your force is 100 kilonewton, okay, 100 kilonewton, and deformation is 1 millimeter. If your additional force is 1 newton, that delta F will be something 10 to the power minus something into millimeters, very small, so that you can assume, right? So that you can assume your deformation is not changed still, right? That's something, right? So that depends on even the conditions, right? So you don't go ahead and apply a very big force and think, okay, how this deformation is not changing, likewise. So always keep this in mind. So you apply a small amount, right? Very small amount, and that extra deformation will be negligible compared to the original one. Think it that way if you can't, right? So overall, we keep the delta F constant, right? And di constant as well then, right? In the first method, we keep F constant and this F constant, right? Here, di constant. So due to this, you will have an additional force of, let's say, uh, delta Fi, okay? You will have delta Fi, right? So what happens is external work done. So you can still draw the curve, right? So I'll draw it here. So now your force is like this. Delta F, and this is F. So now you increase the force by delta amount. So I'm exaggerating this force, otherwise you can't see. If it is a small force, you can see this in the graph. I'm exaggerating, right? So this force will be delta F, right? So what happens is if you keep the deformation constant, so that your additional work done is this part, right? You increase the force. That's what happened, right? So that delta W, delta external work done, is delta F into delta deformation in the actual structure, right? So that the strain energy, total strain energy, will be the summation of strain energy in ith member, right? So that you can write it delta. So it's also like this. F force initially Fi, now it's the force Fi plus delta Fi. Here F plus delta F, right? So the additional work done due to this force is delta Fi into Di, because the deformation does not change, right? So this is the additional force you applied. Due to that work done, similar to this, right? Similar to this. work done di. If you want to clarify, you can just plug di fi to this and delta fi to this, and think initially di deformation, you keep the deformation constant and increase the force, and this will be your work done additional. It's actually the strain energy stored, right, additionally, right? So that's going to be equal as it is. So you can write delta f is equal to so you can actually see these two parts, right? So this is the deformation in actual structure, and this is the deformation in actual structure in members, right? So this is the actual part, right? And this is the virtual part. So this is the virtual member force due to the virtual force, right? Virtually applied load. This is the virtual force applied, right? So within these two methods, we usually use the second method, okay? That is easy. And you can go ahead. So people really like the uh, things getting easy, right? So we can actually do this. We can make this delta f as unit load, right? You can apply a unit load, and then this will be the deformation additionally, sorry, the force additionally generated due to that unit load, right? Multiplied by in the ith member, right? Multiplied by the original displacement due to the original force, right? So in this way, you can easily find the deflection, right, at any given point. And we'll go through. So actually, if you still can't get this equation, this is how we actually deal with this. So we can draw it in two diagrams. So you will have f in the actual structure, right? So fi, and the displacement is di, right? This is the displacement, that is a constant, okay? It is a constant. So you separate the structures into virtual loading. So you apply some virtual load. So always apply a unit force. That's easy then, right? So there will be a force due to this unit load. It will be, let's call this delta fi. Okay. So this is the additional. So let's say this is, there will be delta f2. So let's call this 1. Let's call this 2, right? Likewise, let's call this delta f3, right? So there will be some forces. So what you have to do is you multiply this delta force. So your equation is given by whatever you virtually applied multiplied by the original displacement, right? You virtually increase the load, right? And multiplied by the original displacement in the structure, right? Not the displacement in that particular structure, displacement in the original structure at that point, right? So that will be equal to what? this, so this is delta U, delta W. So this is the external work done, right? This is strain energy in each member, right? So let's say this is D1, okay, D1, D2, the displacements, okay, D3. So the strain energy in ith member has now additional strain energy stored is delta Fi into original displacement, right? This is into original displacement. We know the why. Our assumption, deformation is constant, right? Deformation is constant. So you increase the force, so that means this is the additional. So that means the strain energy stored, right, due to this increased force, right? So that's going to be Di plus. So for second member, I can write delta F2. Let's say the force is delta F2 into the deformation in actual one is D2. Likewise, you have to add. So what this really means is delta F I. This is simple F, okay, into Di. So you're gonna have to remember this is very easy, right? This is for the actual displacement. So the remaining is virtual, right? So you can see if you apply a unit load, that's easy. You are directly taking the actual displacement at the structure, right? So this is virtual. And this is actual. Actual, right? So we'll do an example. So if you need to know the deformation, let's say this point. So the same truss, right? So the same truss, you need to know the displacement of this point, right? So what you need to do is apply a unit force along the direction where you need to estimate the deformation, right? So in this case, you have to apply unit force in this particular manner, right? Okay. So that unit force I will separately write it in this way. And you have to apply where you need to where you need the deflection and in which direction, and on that direction you have to apply a unit load. That's it, right? And then calculate the member forces. So then again this equation, virtual force increased and a virtual work added externally multiplied by the original displacement of that point, right? That is the work done, right? Work done, and you multiply the member forces so by the original displacement in the each member in the actual state, right? Always the displacements are taken from the actual state, because this is also you can find easily. I'll show you, because that's a member. This is a point, right? For a member, you can find the displacement in this fashion, right? If you know the member force, length A and E, so you can easily find the displacement, right? So that this is very easy. So if you want, you can rewrite it using this delta Fi into, so you rewrite it this equation using the member force, actual member force, okay? Fi Li over A. So that's it, and we will discuss an example. So we go to an example. So let's take an example like this. Right. This length is 5 AE. Okay. So imagine you have 5 kilonewtons load, and let's say this length is L. Then this length is going to be L into 45, the angle between these two. So this is L into root 2, this length, right? Right. So call this A, B, and C. I need the horizontal displacement at B. I need to find the horizontal displacement at B. Probably if you just think how this truss is going to behave. So you are pushing it this way. So you want to push this member to down, right? Right. So that means this member will compress, right? So you push it and we'll try to shorten. So that means probably you will be in this way. Is if you consider this as positive, so your B, the displacement mostly will be negative, right? More likely to be negative value. If you apply, think about the original structure, right? How it behaves, right? So this is a virtual direction you are taking that is positive, right? You need this deflection in this way, right? Horizontal displacement in that way. So I'll apply a unit force in that way. If you want, you can even take this as positive, and then you have to take you have to apply the unit force in this way. If you take this as the your direction, you have to apply the unit force in this way. So it doesn't matter. Always take tension positive, or else direction where the member is elongated is positive. That is again tension positive. Okay. So what you need to do is, first you need the member forces, right? First member AB, member AB and BC. So for AB you can take the components in this way. Let's say F1 into cos 45. So you take the components at B joint along vertical direction 5, right? So F1 is going to be 5 into root 2, and that is a tension, right? So this load try to push this member, right? Push this, sorry, pull this member, right? Pull this member. So the member force is positive 5 root 2, right? And then the member BC, okay, the member BC is what happened actually. The member will be, so you can take the horizontal components, right? So So you can take the horizontal components at P. So that F1 cos, no need of cos, actually this is sine, right? So anyway, sine 45 cos 45 usually same, so I always use cos 45, that's why. So Fi cos in is equal to F2. So that's going to be F2, and that's what, because this is in this way for this joint and this is in that way. That's how these two are balanced, right? From this force and this force in the member. So so definitely this is a compression and this is negative phi, right? So now we know the member force and the member uh, respective lengths also can be taken like this. So the deflections also, right? So these are the actual member forces and the deflection. So you remember DI is FL over AE. So we'll consider this is going to be 5 over 2 into L to the power 2 over AE, right? So that's going to be 5 into then yes, 10 L over AE. I think I'm correct, right? Because F into L means 5 into root 2 into L into root 2. So that's going to be root 2 root 2 2, 2 into 5 is 10, 10 L over AE. So this is going to be its L. It's just displacement, right? Displacement is always so this is going to be displacement and it's a contraction actually. So this F is 5 L over L is L, okay, over AE. Let's consider area and E is not going to change, okay. So we need the displacement from the members, right? So you remember we need the displacement original in each member, and if you calculate the member force in for the virtual state, so we have to calculate this one, okay. So we have already calculated these three, right? These member this displacement. If you calculate the member forces due to this virtual load, then you can easily determine delta F, right? So you have to apply a unit force in. So you need to calculate the displacement in this way. So you have to apply a unit load in this way, right? So if you apply a unit load, you will probably notice that the force in this member is exactly 1. So if you take the components, right? So you will probably notice why there is a contribution from this member as well. But just look at the horizontal way. You only have the component in this way, and but there is no load to balance. So that means in this member you have zero load, zero member force, right? So if you have zero component from this is you can be disregarded. It can be disregarded, and if you want, you can take F1 and F2. So F2, let's say theta, F1 into sine theta is equal to 0, no other load. So sine theta is not 0, so that F1 is 0, right? So this load is entirely taken by this member and it's a tension, right? This is 45, okay. So you need the member force. So for member, this is the member AB and BC. So you need the displacements, right? So the displacement is 10L over AE and minus 5L over AE. Why minus? The compression force is negative, right? Okay. So these are the actual displacements. So those are not going to change, right? So your virtual forces, right? So displacement, actual displacement multiplied by the virtual member forces, right? So the virtual member forces, so if you apply 1 in this way, so this is also 1, this is 0. This is 0, this is 1, but it's a tension now, right? It's a tension. So that's going to be your virtual member force, right? Delta Fi. So this is the di into delta Fi, this term, right? Di into delta Fi. I have written di first, okay? So it doesn't matter. So this is anyway going to be 0, and this is going to be 5 minus 5L over AE. And you have to take the summation, so that sigma is minus 5L over AE, right? So that sigma is the total strain energy stored due to that virtual load, right? Virtual loading, right? So the work, actually the stored energy, so that's equal to the, so this is not sigma, this is delta U. So this is equal to the work, external work done by that virtual force is going to be, so you know the deformation is constant, so that you can still take the displacement are not going to change and it's equal to the original displacement in the structure, right? So you multiply virtual force by the original displacement, virtual force by the original member forces, so member displacements, right? That's how you equate uh, virtual force multiplied by the original displacement, that is the external work done, it's equal to delta U. So that's going to be the virtual forces in each member due to this virtual unit force multiplied by original displacement in the each member, right? So that's going to be pi L over AE. So your delta F is this value, because divided by 1 is again this value. So it's negative. So that means you took this way as positive, but the actual displacement is this way, right? Hope you understand that. And this is how you energy method to be used in a basic structure. So this will be a bit different, but the concept is same, but you can use this in beam or frame as well. We'll discuss later, but then next we'll consider the Castigliano's theorem, right? So we'll basically finish these two, right? So this is okay now, right? Because we use this one and we discussed this also, right? This is the commonly used method we discussed with an example. Now we will move to Castigliano's theorem, right? Castigliano's theorem, right? So what Castigliano's saying is, you can actually take like this. I'll show you. So that let's take the same truss. Okay, let's take the same truss, and you had force like this, right? Okay. So you remember the work done was half into delta, right? This is delta F, and if you want, you can write this as, so this is F equals Kx, right? The entire stiffness of the truss you can write, if you want, F over K, right? Stiffness in that direction, right? So you can write this as F squared over 2K. Okay, so what you can do next is that you can go ahead and write the same expression, and actually it's going to be U for U, right? So for U, you can write sigma for particular member, right? Particular member, it's going to be Fi half Fi di into half, right? So you can still write this as Fi. So this is also can be written in terms of Fi Li over Ae into 2. So that's going to be Fi squared Li over 2A. So this is the strain energy due to the axial loading, right? So this is in a member. When you sum it up, the total strain energy in each member, all the members you can take, right? So you can see, so this F is actually due to this capital F, right? So that means F is a function of F, right? Capital F. According to capital F, Fi will change, right? So that's the basic idea. So that U is a function of F, right? So that brings you U is a function of F. Let me check again. So F is a function of capital F and U is a function of simple F. So that you can write U is a function of, so this Fy is a function of F. So you can finally write U is a function of F, right? And clearly W is also a function of F, right? From this one you can write. So this you have to remember. W is a function of F and U is also a function of F, right? So what happens? So in this, just like the second method, we apply a disturbance, we give a unit some delta force, right? So you give a delta force so that your equation is going to be now this Fi F plus delta F, right? So strain energy will be also plus delta F, right? So this is going to be simple delta F, right? No, it's going to be delta F, it's going to be delta F. And you can do the Taylor series expansion. It's not just expansion, right? It's delta and other things. So this is the Taylor series expansion. You don't need to remember these things. So that's going to be Wf plus dabba W. So this is partial differentiation of W with respect to F into delta F is going to be delta F. So you remember W is this function is equal to this function, right? So you can cancel those things too, right? Those two anyway equal, right? So what will be remaining is dabba F. So you can cancel this dabba F term, right? Is equal to what? Dabba U by dabba F. So what this dabba W by dabba F? So W is this, you remember, right? Two K. Where did this come from? Right? Where did this come? Remember, force half into force into displacement. Displacement is written by F over K. F equals Kx, okay? So then F squared over 2K. So you can again, so partial differentiation is nothing different from the usual differentiation. Only thing you subject it to the correct subject, right? So F is differentiated, that's going to be 2F. That's it, right? Partial derivative. So this is going to be F over K. So you know what is this F over K? Again, that's going to be delta F, right? So this gives you an interesting result, that is delta F, right? Dabba F by dabba. So that's going to be this result. So that's give you. So that's how you link two theorems together, right? So Castigliano is saying if you differentiate partially the strain energy with respect to the force on that direction, you are getting the displacement. You are getting the displacement. That's the simplest meaning, right? So this also, this is the Castigliano's theorem, right? This is Castigliano's theorem. So we'll do the same example. In that case, you can't apply a unit force because you have to differentiate it with respect to a particular subject, right? Particular variable, so that you can apply a force like P, right? So we'll take the same example. Since you already know the member forces, I will not write the member forces, okay? I will not find the member forces since you did the same video previously we did. The member forces, I can write the members A, B, and C. I need the displacement in at B along this way, right? That is positive, and tension is positive. Tension is positive. This is A. Okay. So beam support, right? So what you know is, if you apply a load like this, so the member force will be AB and BC. That's going to be member force. So the original member force is okay. It's going to be AB is 5 into root 2, you remember, I think. This is minus 5. The same example we did using this, right? So here I'll show you. Yeah, this one, okay, it's the same example. So what you need to do is, delta W is W by W F, right? So you need to find the total strain energy, right? Total strain energy you need to find. So how we are going to do that? Now you have the forces, right? Let's say so this is how you do it. You need to find in this way. So you need to, now in the virtual work method, you apply a unit force. Now you have to differentiate it, right? So you apply some variable on some subject. So let's say P, we apply a P force so that you can differentiate it with respect to P, right? If you apply Y, differentiate it with respect to Y, right? Okay. So P, right? So if you apply P, right? So your new member forces, right? So I call this Fy star, right? So we don't actually need this, okay? We need this one, okay? So what happens is, so it's like superimposing, right? You can take this into two structures and finally add the values if you want, or else you can find the value using same structure if it is not complex, right? So here it's a compression of 5. It's a tension of 5 into root 2. So you remember, you apply a unit force in this way, you remember this force was 0, right? Using virtual work method, so the same happens. This is a tension of P, right? So the total, if you apply both these, so that's going to be P minus 5. This is a tension, this is negative 5. So that's actually a compression. We have written this as a tension. Tension is a negative compression, right? So P minus P, 5 minus P. If you take this into in the same structure and find it, you will also ended up with P minus 5, right? So that's going to be tension P minus 5. Sorry, it's not in the first member, it's the second member. This is going to be anyway 5/2. That's tension. This is going to be P minus 5, right? Okay, P minus 5. Okay. So the total strain energy, right? Strain energy stored in each member will be, right? So you can go ahead and so U in the first member. So this W will be Q1 plus Q2, right? So W by, so I'll set this U. So you have to differentiate it with respect to P. So that will give you the deflection along this way, the delta, right? Say delta P. Okay. So we need that way, right? So we take the difference, right? We apply the virtual force of unit load in the virtual work method. Now we apply a P force, and we take and differentiate the strain energy with respect to P, right? So how we can do that, right? So you can see this, right? So now you need to find what is this W by W. U was actually, you remember, U was sigma, this one, sigma Fi Li over 2Ae, right? So that you can W by, let's say W by F. So this is sigma. So you can take this W into inside. So you know F is a function of F, right? So you can differentiate it with respect to F easily. That's going to be 2F1. Since this is a function, you have to multiply it by da by F over da by F, right? As well. And then 2 into AE, right? So you can cut this term. So what you really need to do is you have to take the Fi value, original Fi value, and then take the DABA value, right? Sorry, this is not L squared, okay? Right? So this is Fi, right? So I'll write this again as F star, okay? So this is the original F. Right, this will be important when the table comes, right? So this is W. So actually you can see right there. So this u is a function of each member force, and you can derive an expression like this, right? So this term is what you need, right? This is da by u by da by f, right? For each member you have to do this, right? For each member you have to do this and calculate. So we'll take a table. So this is the member AB and BC, and the Fi, this is the original force, right? Remember, so this was 5 root 2, this is minus 5, right? So F star was, this is when P is added, right? So when P is added, so you can see this is not going to be changed. Is P minus 5, right? The tension is positive, okay? So this is now very critical. This is du by dp is, you can written somewhere like, so this can be related to df over df, right? Da by u by da by f can be related to da by f by da by f. So da by u by da by p then equal to da by f by da by p, right? So this is going to be not original force. This is very critical. I wrote it in different color. This is da by, this is da by f star, okay? F star by da by p, right? So if you differentiate it with respect to p, there's no p term, so this is 0. There's only one p term, that's going to be 1 minus 0, so that's going to be 1, okay? Okay, so Fi, so then you will have L over AE term as well. So your L is, I think, this L root 2 over AE. This is anyway L, right? So finally you need to multiply what? The original F. So I'll come to this force da by F by da by P L over AE. When you multiply F, which F is to be taken? You always take the original force, right? You multiply it by the this one, and that is multiplied by this one. The original force, not F star, but you have to multiply it by dF star over dP, right? Into L over AE, right? So anyway, you have 0 here, so the total term would be 0. You have F, not this one, okay? Not this one, you multiply finally, right? You have to take that the structure with P, and you can take the member force and you take the derivatives. Those derivatives are the things which is going to be multiplied by the original member force, right? Original member force. That's why you need original member force at last, right? These two are for the derivation purpose, right? Derivatives. You need to differentiate with respect to P and multiply it by the original force, right? Not these forces, okay? You multiply it by this and multiply it by this. right? So this is L over AE. So that's going to be minus 5L over when this is U actually, right? Strain energy ith member. So you can write U as sigma of UI. That's going to be, when you add these two, that's going to be, sorry, this is actually UI over UJ, UP, right? So that's going to be delta UI, delta U by delta P. Right, this is going to be phi L over AE. So this is sigma of each member. So that gives you total strain energy differentiate by with respect to the force, right? Virtual force in that way, right? So that is going to be what? Going to be your deflection, right? In that way. So what's that? Minus phi L over A E. So you can see it gives the same answer, right? So understand the fundamentals. What's done in the virtual work method, you apply a unit force separately and multiply it by the unit member virtual forces by the original displacement in that members, and that's the internal, sorry, the strain energy stored, and you equate with the external work done. Here what you did was something different, but same thing relates to the strain energy, right? So this is Castigliano's this is Castigliano's theorem, right? So I'll highlight it. This is Castigliano's theorem. Okay. When you differentiate it with respect to the force applied, that give you the displacement and the on that direction, right? In that direction, the displacement along the applied force, right? So we apply not a unit force this time because we have to differentiate with respect to that force. So you will apply a P force, right? And differentiate it with respect to P then, right? So multiply that differentiation with the original force and L over EI term. So that gives you F, this da by F by da by P, in here F, but in the example P by L over EI, that gives you da by U by da by F in the ith member. Sorry, so that gives you the ith member. So when you sigma it, right, take the summation of each member, you will get the total strain energy with respect to the force applied. That gives you the displacement, right? So hope you understand. Thank you. So we have now, please check the channel. We have finite element method, right? Lectures, FEM lectures from the beginning, and then moment distribution, everything there. If you want to learn SAP or ETABS, those are there, right? SAP or ETABS, the softwares, those are also included. And then the matrix structural analysis, right? Matrix force method, matrix displacement method, everything there. You can check the channel. All the videos, I have numbered it correctly. So you can go from the beginning, okay? So if you have anything, you can just email me, okay? Thank you very much.